Okay. Hello, everyone. Good afternoon. Before I start the lecture, there is important information that needs to be clarified. So, first, let's look at our blackboard, okay? I made an announcement on March 18. I have posted the final groups with the corresponding institutions. It is time now to coordinate and choose the program or reform that you want to analyze, change, or improve. Okay? So that was my announcement. And that's what you have to do as a group. Once the group is ready, institution is ready, you all get together, and by doing what I just mentioned in this announcement, you will better understand what that institution does. So you go to the World Bank website or the IMF website, you are going to learn what they are doing and from what they are doing, you're interested in as a group and you want to study, analyze, change, improve. Okay? Good. So now let me talk a little bit about next lecture. Unless you have any questions. Have any questions? Concerns? So next lecture will be special. So next lecture we'll try to do what is called blended learning, which is a type of teaching that tries to make our teaching experience more interactive. So for that, all of you and the ones that are listening at this at home in the future, ideally, everyone has to come today, okay? Next week. Because next week, we'll have about an hour where you and your group mates, are going to get together, are going to talk and make progress on the reform and project you are analyzing or you're studying, okay? So you're going to get together, have a conversation. I'm going to be around. The tutors are going to be around helping you, giving you feedback, asking you questions. And after that process, we are going to present. So I'm preparing a presentation for you, me and the tutors. We're going to give a presentation that's supposed to be like a presentation we're expected from you. So we're going to be three, Jean, Jose, and me. So we're going to present each of us 60, 90 seconds. About that, if you want to present 2 minutes. The whole thing is that we have enough time for the tutorial to end with all the groups presenting. That's why I prefer 90 seconds presentation on average, okay? But we're going to give this mock presentation next week. So you realize you're going to be able to participate, ask questions, give feedback the same way we are going to give you feedback and ask questions in the day of the presentation. So and please also come here to learning resources, to assessments. If you have questions about the project, the details, there should be in this Word document over here. If you still are unsure or have questions, email me, please. What else? So then after we give this mock presentation and you have a better idea of what you have to do, this is part one of the project, 10% of the course. After that, I will go over the mock exam solution. Who has seen the mock exam already? Who took a look to the mock exam? So in the last 30, 40 minutes of the next class, in the lecture, I'm going to solve some of the questions. It's going to be like, I'm going to ask you which questions you would like me to solve, and we're going to do it, okay? We're going to discuss about the potential solutions, not in so much detail, so we kind of cover the whole thing. That's one thing. So here, in this Word document, you can see more details of the part one of the project. Questions? Okay, so now, part two of the project is going to be based on a paper that we'll discuss in lecture 5 but not the actual lecture 5, because we're going to allocate time to work on the presentation and the report in the actual lecture 5. So what I'm going to do, and this is part of the blended learning experience, and I'm missing the course tools right here. So the other important information is this. You come to learning resources and give it that in week 5 or lecture 5, we're going to have this special session, more interactive, ideally much more interesting. You're going to have us presenting and you're going to be giving us feedback about that presentation. But you still need the slides and the video recording for lecture 5 of last year. So I could have done this. I could have just give a talk on a next class on the empirics of growth, and you have time to do your project part 1 by yourself, or kind of have the slides there, put the video recording there of this lecture, and instead working on project part 1 in the class. And I prefer that because I do think that working on presentation skills, the soft skills, not just rational, but emotional intelligence is super important, the way you relate, the way you make your arguments, etc. That's crucial. So then, here you will find, look at this, the slides for lecture 5 next week that we won't cover in lecture. They're going to be there. And these are important for the project part 2. Right? The project part 2 is completely empirical. You have all the instructions. I'm even giving you the Bain database, so it shouldn't be that bad. But it's going to be quite interesting because you're going to be using data. You're going to be testing the models that we have studied. And here, I also posted for you, in case you have questions, you don't understand the slides, I posted the video recording from last year. Okay? So you can download that MP4 file and listen to the last year lecture on that. And in this particular lecture, it's exactly the same as the one that I gave in 3020, which is Advanced Macroeconomic Undergrad. In this regard, it's exactly the same in the empirics part. Okay? So you have those two things to study as well, and it's going to be useful for the project. And then in the actual lecture 5, next week, we're going to work on project part 1, as I said. So please, everyone come. Coordinate with your group mates, and even the ones that are not coming and are listening from home, try to come as you can make good progress on the project part 1. Okay? Is that clear to everyone? Any questions, any concerns, any feedback? Yes. Yes, so it's going to be the same group. The same groups are going to be working in the project part 2, and that's completely empirical. So there you're going to have the challenge of allocating different tasks, data collection and data analysis, writing, etc. So it's going to be all this. And the interesting part is that you will be testing the models. You will be testing the models that we have been studying so far. Okay? Any other question? Any other concern? Yes.
Will there be any more guidance on the exam this semester?
Like the answer, you mean?
Just like what we should be studying or...
So the mock exam is very representative of what you will find in there. And the mock exam is based on the lecture notes. So if you're able to follow the lecture notes pretty well, that should be fine. If you have trouble, consultation of course, but also the book. The lectures follow the book quite closely, and the book of course expands on the lectures. So in that sense, it's kind of boring because it's going to be pretty much to what the lecture have and similar to the mock exam. Of course, not the same questions, but that's what I'm expecting from you. Is that clear? Yes.
Is lecture 5 examinable?
Sorry, say that again.
Is lecture 5 examinable?
Lecture 5, yes, because that's crucial for part 2 of the project. The project, part 2, is empirical, right? You're going to collect data, all the instructions are there. But that part of the project is based on those slides. In those slides and in that video, I go in more details on those papers and those empirical analyses. So this is useful for project 2. No. So it's just my answer. This is important just for the project 2. It's not for the... In the exam, you won't play with data. So this is a better way to say this. There, you don't have more lecture material. There you have just empirical analysis that test the theories that we have studied. But we will study until today, basically. Okay? So there is probably some few new things, but those are not going to be tested in the what is going to be tested in the mid-semester exam is only until today's, only up to today's lecture, okay? Yes? To the tutorials? You think, is that a affirmative or question? They are similar. They are similar. So tutorials, mid-semester exam, the actual exam is all kind of similar. Of course, different, but you won't find much surprises. Okay, so it's going to be if you work on solving the mock exam and the tutorials, you go to consultations, you should be super fine. Okay, so I'm giving you some things to work on. If you work on in that mock exam, if you work on that, you should be very fine in the exam. Okay? Does that make sense? More questions? Okay. Who finds the mock exam hard? Who finds it hard? 1, 2.
It's just a little tricky.
This what?
Just a little tricky.
It's tricky? Yeah, there are some tricky things. So that's the idea, right? But if you find that the questions are not clear or something like that, let me know. Okay. Good. So now let's start the lecture. We will continue with the augmented solo model, and after that we go to the endogenous growth model. Is it volume right or is it too loud? It's right? I think it's too loud. What about now? What about now? How do I do what you ask? Okay, let me mirror that, my iPad to this, so I can start with the lecture. Okay, who already chose the program or the project you want to study analyze? 1, 2, 1.5, 2.5. Okay, remember I showed you the announcement and I said after you chose the institution, you should get together and choose the project or the program. Another question. Nobody asked this, but I know you're wondering this. Should the project or the topic be related completely to the class lecture? What do you think? I wasn't very specific on that. In project part 1 I said study things, reforms that have effects on GDP per capita, the welfare of the economy, but it wasn't super strict. So if you like something a bit different, and I said this during lecture, I won't be super strict on that, and I will be happy to listen some things that are out of the box. Of course, economics, right?
economics. Ideally macro, but if you're interested in microfinance or something like that, like some credit to some households or firms, that's actually in a given country, then that would be also interesting. Okay? Does that make sense? Okay, let's recap. So we have studied the augmented Solow model that has labor productivity growth, the Z parameter. And today we'll finish that model, and then we'll start studying the endogenous growth model. Okay? So we learned that a simple extension of this simple basic Solow model is able to match some facts in the data, like for example the fact that GDP per capita, the wage rate, they are growing at a trend that seems to be quite similar and seems to be close to that little Z. So those graphs, we saw it last time. Today we're going to finish analyzing that model, like how shocks affect the long-run equilibrium, but also how they affect the transition. And here I want to make an important point, like typically the way you study the Solow model in class before, you study the long-run equilibrium, and you go from one long-run equilibrium to the other long-run equilibrium. What we do different here in this course is we're looking more at the transitional dynamics as well to try to understand what happens with the wage rate when there is a shock, whether the marginal productivity of capital or labor increase, decrease, there are these complementarity. So we also look at the impact, short-run effects, the transition, and the long run. So in that sense, it's a bit more complex, also in terms of the math. And today we're going to study the endogenous growth model, which is going to be more interesting because the Z term and the A term are not just exogenously changing. They change because there are more researchers or because there are more computers allocated to the R&D sector that then creates ideas. So that will be a richer model that is sometimes past students ask me to teach that model much more in this course. I would really like to, however, maybe in the future I'll do that. Okay. So let's come back and look at this graph, okay? So what we have in that graph is our TD equation. And our TD equation in the most general case this is actually our TD2. There is a noise, right? But it's not this mic. Okay. Remember, we have our TD2 equation that the reason it's called TD2, it's because it has over there variables in hat terms. So remember, let's redefine this. And we have that little k hat is just big K over Zn. Why do I divide that big K by Zn? Why do I do that? Why do we have to do that?
In terms of per capita, but you also, in this model, you want to account for efficiency. So you get Z.
You account for efficiency, that's right, but why do we have to do that? Why do we need to do it? Not exactly. Huh? Yes. So to find a long-run equilibrium, if you don't divide by Z, you won't find a long-run equilibrium because things are going to be trending up. So by definition, steady state is something that is constant. The only way you can do it is by removing things that are growing. So we divide by Z and N in order to remove trends and find a variable hat that will indeed have a long-run equilibrium. So technically, that's the idea. And then we're not interested in that variable per se. We are interested in per capita variables. So then after we do this, we solve it, we look what happens in terms of the little hats, But also then we come back and study and understand what happens with the per capita variables. And how we do that, we do it by just doing this very simple change. Just by working out that equation, right? Work out that equation, and from the right-hand side, that little z in the denominator goes to the left-hand side, and then you get just big K over N, which is little k. Okay? So this is just a very simple review for you to understand why we do this. So you might find why we're doing all this complicated math, dividing by this, multiplying by 1 conveniently, etc. That's convenient. It's a convenient way to find our long-run equilibrium. Because that's the only way we're going to find a long-run equilibrium in this case. We're going to find an intersection over there between the TD equation and the 45-degree line. Okay? Good. So now let's study, last class I think we studied the shock to little s, so the saving rate. So now we'll study what happens to the model when there is an increase in total factor productivity A. Here A, remember, we have a production function like this, where there is an A, F, K, Z, N. So if A increases, that means that for any given amount of inputs, for any given amount of computers, for every given amount of workers, the firms are going to be able to produce more goods, right? So that increase in productivity has an effect on impact right away on our production. This is suppose that, and this is the thing about the exogenous growth model. We don't know why this is happening, but it's just happening. Before the class started, somebody came to me and he said, you know, I just discovered a better way to teach your students. And he told me that. And I just apply it, and you learn much more than when you would otherwise. So we're assuming like that exogenous change in productivity, okay? Later, in the endogenous growth model, it's like there is a group of people out there working on better teaching techniques. And they are out there working, there are some number of lecturers there, some amount of computers that are designing this, and that might take time, but when they find it, then it's going to affect the delivering of a lecture for you, okay? Okay, so what that means is that our TD equation is going to shifts up like in the saving rate. Why? Because we have a technology parameter over here in that little circle there, blue circle. If that increases for any given little kt hat, there is a larger little kt hat t plus 1. And then that implies that we go from long-run equilibrium 1 to a long-run equilibrium 2 here in the new intersection. So as I said before, these models are typically taught in a way you go from 1 to 2 without caring much about what happens in between, right? But here, we do have our equation that tells us what happens in between. In between, there is an increase in A. What that implies for consumption and investment. Consumption and investment are going to increase on impact. It's like suddenly, how do we put that in words of, say that no, it's a bad example. I was going to link it to the teaching, but it's really hard. Suppose that you just have more income. Today. That means that today on impact, you have more income and you're going to invest more, because investment is just a fraction of your income. Investment is just IT, little s, YT. So on impact, there are more production out there from firms. That's also higher income for you. And then, because you're working there, and then in the economy there is higher investment, and there is also higher consumption. Okay, so this is going to go up on impact, and consumption as well is going to go up on impact. Sorry. Yeah, that's right. And then what happens to capital stock? Investment is like you're going to buy some computers or some materials, so you build up, say, a classroom. And that's an investment. That's something that's going to last there, and you can produce teaching in there. You can provide teaching. You can provide it's like a meeting in a company. You're going to produce in that meeting. You're going to have meetings. You're going to have production out there, whatever is what you deliver. So then that's going to increase, but not today, tomorrow, right? So we can analyze the effect of these shocks on the variables in per efficiency unit first, just to have it clearer. It won't be exactly the variable we care about, because as I said before, we care about per capita variables. We don't want to, this is our big Y, and this is our big Y, the little Y hat. What if a policymaker cares about little y hat rather than little y? What would you think? Would you vote for the left or the right politician? Maybe the left and right are not necessarily. What would you vote? The left or the right? Who votes for the right? Who votes for the left? Oh, that's why you were looking at me before, like, we need to account for skills. Okay, so the left one is going to say, I'm going to try to give more. Basically, I'm going to try to maximize output per efficiency unit. So I consider how skilled you are or that. The other one is just saying, regardless as you are, if you are really good or really bad at your job, or really productive or unproductive, I'm just going to count heads. That's the second one, the right one. I would also go with that one, just to be, it's interesting. If you maximize what you give to people based on skills, that's going to be complicated. Okay, good. But we start with that. Okay, yes?
Capita,
yep.
But then because you pay them more, the inflation increases.
What increases?
Inflation.
Okay.
Because they have more buying power now. And that leads to equilibrium of some kind in this model.
So you're thinking of having a model slightly more complicated with two types of people. The thing is that it's tricky here because there is just one representative household. So we're just thinking of one person. So the question I ask you is not directly applied to this, because this is just one person. If that person became more or less productive. But what you're thinking is quite interesting in the sense that you separate the world. There are some guys that are super productive, or others are less productive, right? And you're thinking of what is the effect of having, this is not working well. You're thinking of the inflation effect on paying more to the more skilled people, right? That's your worry.
But then the consumption stays the same because in producing it, they sort of get more wages, but at the same time, because they get more wages, everything is more expensive. So it's sort of in real terms, maybe comes.
Who wants to? This is an interesting point, and we're going to discuss this later next week in the slides that we have. But also, let me give 5 minutes to this. What has happened with wage inequality in the last 40 years? Increasing, right? In the U.S. And so many researchers trying to find why that is. Some people say that financial deregulation that increases the wage of the finance people, or say that intellectual property. Patents, yep. So that would be patents. Others, What's going on with this? Others argue that this is about technological change. There is skill complementary with high skills. Like when we talk about the robots, if we are complementary to robots, but most people is not, then inequality is going to be. My point is that inequality has been increasing a lot, right? The wage of the high Z over the wage of the low Z. That's been increasing. But what has happened with, what's your name? Vivek. What has happened with Vivek point about inflation? Has inflation also trended up like this? No, right? It's actually been like this and like this. But mostly because of central bank policies, say here this is the 80s, right? But it still is interesting, maybe what you're thinking about is more of about like the purchase power of households, like the W over P, right? That's what you're thinking. And who read an open letter from many economists in Australia this week? There was an open letter, but many economists from Australia, one from UQ, they are concerned that in Australia, W over P is not been growing so much, which is potentially very linked to what you're talking about. I mean, it's interesting. So the fact that the wage growth has been declining. So before like 4%, and now it's like 1.5%, and that's like a measure of welfare, right? What you can buy with your salary. And they argue that that hasn't been growing so much over time. Is that linked to inequality, as you're suggesting? They are proposing some measures to overcome that. One of that is increasing the minimum wage. And I will be talking about next week with the tutors, whether that increase in minimum wage or some other things that they are proposing are actually in line with what they're actually in line with actually mitigating the decrease in the growth rate of wages. And now that I forgot your name, Ravik? Vivek. Now that Vivek mentioned that, it could be really interesting to think about this through the lens of that. Another thing that is pretty obvious is market power, right? So market power, increasing prices. Okay, so this is a very interesting topic, but again, in this model, there is just one representative household. So it's super limited for us to think about distributional issues, right? It's limited. But we could, that in the test you would probably have something like that, thanks to you. No, I'm just joking. You won't. Okay, so now we look at the variables in per efficiency units. Capital doesn't change right away because it's installed already. Computers, seats, chairs are already there. But given that investment increases as productivity increases income and then investment, then there's more capital tomorrow, right? So that's going to increase capital, and it's going to be in a concave way due to diminishing returns, right? So this concavity here is like you invest more, you keep investing more, but at some point capital is not so much profitable as it was because of diminishing returns, and eventually you just converge to a new level of physical capital per efficiency units, which is a higher level. We saw that in the previous graph. When you shift this curve, you go from 0.1 to 0.2, higher level of per capita capital per efficiency units. Okay, so here, and then output on impact, as we said, this little way ahead is just this. Then on impact, more productive firms will produce more right away, and Y increases right away. So this is that jump that you see there. That jump is important. Understanding the dynamics of the model is important, but also, again, focusing on the long-term impact. So the dynamics here is that it's no on impact effect of capital because it's installed, it's in state variable, already there, stock. However, production right away increases when we are more productive, and that's a jump at period 0. So suppose that this is the period 0, T0 of the shock. At T0, when the shock happens, you increase right away production. And then, after you increase production over here, you keep producing more because there is more capital accumulation, and capital is a key input for production. But then you reach the new level of steady state output per efficiency unit. Does it make sense to everyone? Questions about this? Okay. Let's go then to the next slide. This is the effect on consumption. They directly depend on output, therefore it's super clear here. It's not like in the saving rate case where consumption might decrease or increase in the long run, because there are two effects. Here it's super easy and direct. We have more money, we consume more, a fraction, but another fraction goes to investment or saving. That's straightforward, and then there is also this concavity. So now once we solve this, now we need to think about per capita variables, because that's actually what we care about in a world where we don't discriminate by skills, where we just want to maximize output per capita or per worker. Okay, so let me come here and then we come back to the... What we saw before is that by definition, this little k is just equal to z little kt hat. Right? So we know that just from the definition of these variables. Therefore, what we know is that if you look at the right-hand side of that equation, when we are in the steady state, at steady state, this guy over here is constant, it's not growing, right? So little kt, let me clear this up. Little kt. So then the amount of computers per head or per workers, little kt, in the long run equilibrium, when you already reach the equilibrium 1, in the previous graph, we already reached this equilibrium. We are here in that equilibrium. When you are in that equilibrium, little k hat is not growing. Therefore, the only reason this little kt, so the amount of computers per person, is growing is because of ZT, right? So ZT out there, how productive is the labor? That guy is growing over time. We are assuming that it grows at a rate equal to little z. Therefore, that is going to be growing, and we can see that from here, right? In tutorials, you discuss why we look at the log of k and not at k. If you had trouble following the math of that, it should suffice. It should be okay still just thinking this way. These variables are growing at a constant rate. If I just draw that graph in levels, it's going to be like a convex graph, growing and growing and growing in a compound way. But if I draw the log of that variable, take the log of that variable that is growing at a constant rate, that's going to be on a straight line with a slope that is approximately that constant growth rate. Therefore, in the long run, as little k, little y, and actually the wage rate are growing at a rate equal to little z, graphically, the log of k looks like something like this as a function of time, where this is little z, and that is time in the x-axis. That is why we take a log. We take a log, we linearize this, and we just see clearly that that variable is growing at a rate equal to little z. But what happens, it happens that actually there is an increase here. At this time, there is an increase in productivity, A. that increase in total factor productivity, the productivity of the two factors, not just the Z, which is how productive it is the labor, that increase is going to increase investment, and then it's going to increase capital. That guy as well, right? So, but that's going to be next period. That's going to be next period. So that is why you go from here to here. The reason you go to that point over there instead of, suppose this is t plus 1. If nothing else happens, you're in the long run path, you would be over here. That would be your situation. However, the increase in productivity makes everyone have more money to invest more, accumulate more capital, which means that you were actually going to be up here with a lot more capital per capita, and that you can see from the formula over here, right? That little kt is increasing because of zt, but also because of little k hat t. And now little k hat t is increasing more due to high productivity, therefore the log of k. And this is going to be like a concave increase, then diminishing returns start to apply, and then again, when the economy reaches the long run equilibrium again, it's again growing at a rate equal to little z, the same little z. Is that clear? So it increases t plus 1 more than what would increase without that shock, right? And then it will then come back to be growing at a rate equal to little z when it reaches the long run equilibrium. Is that clear? Good. So now, with log of y, what happens is quite similar, except that we have the jump. As little y is just z t little y hat t, the jump in little y hat, it also makes little y t to jump. That is direct from that relationship. And then again increases in a concave wave until the slope of this is z because it's growing a little z and z, little z. Okay? Questions? So before the break, I'm going to show what happens to factor prices. This is what happens to per capita variables. To consumption and investment is going to be something very similar to YT. Once you figure out little k, you can just figure out YZI. Most of the time, the evolution of output and consumption and investment will be different from k because they could jump. K won't jump unless there is this huge storm that destroys all the capital in the economy. Now let's go to the wage rate, and here. The wage in this economy is determined from firms that are maximizing profits out there. There are firms maximizing profits, and when they maximize profits, their maximization condition is that whatever they pay to the workers that is given out there is determined in the market. That W has to be equal to A delta F K Z N. So that is the marginal productivity of the worker. For the firms to be maximizing profit, they, if they're smart enough in that situation with no market power, just price taker firms, they won't be changing the wages, they just take the wage that is out there. If I want to hire an RA, I will look at what is the price of an RA, or what is the wage of an RA, and I just stick to that. There are so many RAs out there, there are so many lecturers asking for RAs, that I won't be able to affect that wage. It's just take that wage as given and pay to an RA in a way in an environment with competition. Okay? So then what happens is that, as we saw before, the wage is growing at a rate equal to little z here. Why the wage is growing at a rate equal to little z in the long-run equilibrium? It's because we assume that the workers are becoming more and more productive over time. We are assuming that's happening with z, right? Which is consistent with other facts we see, that the wage rate has been increasing. In the US, we observe that output per capita, capital per capita also growing, consistent with a model like this. But then what happens is that there is this increase in the productivity of the worker, and increasing A not only increases the productivity of the capital, but also increases the productivity of the worker right away. Remember that A is total factor productivity. So then that increases the factor payment. Factors are going to be paid much more now, given that they are more productive. On impact, there is this increase. On impact, from here to here, there is this increase. And then, what is going to happen, that capital accumulation increases, then we have that eventually when the economy is again in the long run, the wage rate keeps growing as Z. So the discussion about what we were talking about, the wage, the inequality, or the average weight of the average growth rate of the wage, what our model predicts about that? It predicts that it's all driven by little z. And what is that? It's just an exogenous value. We just take it. If we were to think of this model and discuss that open letter of Australian economists asking more an increase in the wage, growth rate of the wage, then we should be thinking of things that affect that little z. Right? That should be through the lens of this model. We would be thinking about that. Right? Although this is just an abstract model, there might be much more more things that are going to be relating to the wage, the growth rate of the wage. But that's just to connect things. And finally, the rental rate of capital over here, that's interesting thing happening over here. And what happens is that R, the rental rate of capital, what is paid to the machines or to the computers when you rent, or when you rent an office in city, that is also going to depend on A and on this. Right? So on impact, there is an increase in A, therefore there is an increase in R, and you go from here to here right away on impact. There's an increase in the rental rate because machines and computers all are more productive, meaning that they're going to be demanded more from the firms. The firms firms will demand more of this more productive factor. They're going to produce more. They're going to demand more. This is demand, basically. This is demand. Inputs are more productive. I'm a CEO. Okay, let's get more of this input. Let's produce more. Let's maximize profits. But then there is something else happening there. You supply. Suppose I'm the CEO. I have a company. I want more of these computers that are more productive. But then you, as households, are going to receive more income. Are going to be richer. And then what you do, you start investing more on these computers. You're going to buy more of these things. You're going to do it because you're going to rent it, and you're going to get a rental rate. You're going to earn some income. When you do that, the supply of these computers, these machines, increases. Therefore, the price that is going to be paid to those machines decreases from a supply side effect. Okay? So then, in this graph, what's going on is that due to higher capital accumulation over time and due to diminishing returns, there's going to be more capital accumulated. There's going to be an increase in capital accumulation that decreases the rental rate due to diminishing returns, because that guy over here delta F delta K, the marginal product of capital decreases as we have more and more machines, right? That's one of the assumptions, and intuitively we discussed how that makes sense. So then at the end, in the long run, the rental rate is going to go down, and it could converge to a higher, lower level. Here, it's coming back to the same level. And that is a special case for Cobb-Douglas. It's actually exactly coming back to the same level. The supply and the demand side effect, they cancel out, and at the end, the long run rental rate is just the same. Okay? Good. So now let's take 6.5 minutes break, and then we continue.
Okay.
We're back. Okay. So, during the break, I was asked about how do we know and how can we figure out what's going on with the wage or what's going on with the rental rate. In the test, like in the mock exam, I will give you a production function, I will give you an F. So I will give you suppose a Cobb-Douglas production function that is going to be something like this. Right? So there, we can just calculate what is the wage rate based on that. Sorry. Then we can do this. A times delta F delta N. And that is going to be A times 1 minus alpha K to the alpha Z to the 1 minus alpha N to the minus alpha. Does that make sense? So we can take a derivative with respect to N, to the production function. When we take a derivative, think of this over here like K to the alpha, Z, actually Z to the 1 minus alpha, and N to the 1 minus alpha. Separate the Z to the N, and then it's just N to the 1 minus alpha. When you take a derivative with respect to N, just bring the 1 minus alpha down, and then subtract 1 in the exponent, and then you get minus alpha. So then what happens is that reorganizing terms, you realize that that guy over here, Z to the 1 minus alpha, is just equal to Z times Z to the minus alpha. Because exponents are added, so you can separate that out. And by using that, the wage rate then can be written as A, 1 minus alpha, little k hat to the alpha, and little z. Rearranging all the terms that are to the power of alpha, that will give you little k hat actually. It will be big K divided by z divided by n, all that thing to the alpha, times little z, times big Z. So in that expression, if we are in the long run equilibrium, we know that this expression here, that little k hat, is constant in the long run. So wage is not growing because of that. It's not growing because of that. Alpha and A, they are parameters that are not growing over time. But this guy here has a time subscript, and that's growing. So from that formula, when you take that derivative and you reorganize terms, you realize that the wage rate is going to be growing at the same rate Z is growing when you are in the long run equilibrium, because little k hat is constant there, it's not growing. Okay? So this is part of what you will be doing or did already in tutorials, part of what you will be doing also in the mock exam when you solve this, and basically it's taking a derivative with respect to the factor, in this case n. It's just taking that. Okay? Now, we're going to start with the endogenous growth model. This endogenous growth model is quite interesting because it gives you a way to understand the world, not just based on what happens to this A or Z variable exogenously, but it's the richer model that it has a research and R&D sector. Okay? So let's get straight to the model. This is the last class before the midterm, and then this is going to be evaluated in the midterm. Therefore, let's get to that model. The learning resource for this model is Romer, David Romer, Chapter 3. However, what is in the slides, what is in the mock exam should suffice, should be enough, suffice. I said suffice before it's suffice. Should suffice. Okay? Okay, so let's now add extra ingredients to the model. We're going to change the environment, and the idea here is to make our A, variable A, and Z endogenous. So by endogenous, we mean they change because other variables in the model are changing. Other variables that might be changing endogenous as well, or some other variables that might be changing exogenously, but we're going to put more discipline on what happens to A, to technology. Or Z, we're not going to be distinguishing between labor productivity or total factor productivity. We're not going to be thinking of one technological variable that is going to be called knowledge. It's knowledge, okay? Or ideas, or technology, or knowledge. 3 different definitions. Households still are going to be investing a fraction of total income, S of Y, very similar. However, we're going to be disaggregating this economy, and we'll have not just a final goods sector. There's going to be not just the production of Y. Y before was this production of computers or automobiles, vehicles. It's now going to be the production, also the production of ideas. We're going to have 2 sectors. We have the usual final goods sector that produces Y, but besides that, we have this sector produces Y, but we also have the production of knowledge, A. Okay? 2 sectors. And the production of the sector, the knowledge sector, is going to spill over directly to the production of Y, because that's going to be similar as it before. The A is going to be affecting the productivity of the production of Y. Okay? Good. So let's go to the environment more in detail. Okay, one important thing. We're going to be working at continuous time. Who has worked in math with continuous time before? Okay, so we're going to be making some points over there. Now, we don't have yt, we have y of t, right? So we have, now we have k of t, and before we had kt. On the right-hand side, we have discrete time. That t over there is a month, is a quarter, is a year, whatever is the data available out there. that on the right-hand side here. That is going to be year, month. It has a clear connection with what the data is actually defined. But then we have continuous time, where this t is going to represent a very small amount of time. Think, for example, like a second. It's like instantaneous changes in time. And this mathematical change is useful because there are some properties of continuous time that simplify things a lot. And then in this, one of the things that we're going to be thinking about is that we're going to define k dot of t as the change in the variable. Like before, we had kt plus 1, or no, kt minus 1. That change, which is also you can define as typically delta kt, like the change in k between a month or 1 year, right? That now is defined as k dot of t. This is delta kt, so the derivative of k with respect to time. These are going to be similar things. Like in continuous time terminology, dk dt is a change in k over time, like in a second, in a unit of time, right? In continuous time. And that's what we call k dot. In discrete time, that is delta kt, which is the difference, kt minus kt minus 1. So what I'm drawing over here, writing down over here, are two ways. It's a way to compare discrete time with continuous time, basically. So this is going to be continuous time. Is that right? And discrete time. Okay, this is just a notation thing. And it's useful. One, Romer has this notation, continuous time, so I'm going to follow him. And on the other hand, it simplifies the math quite a bit sometimes. Okay. Is that clear? Good. So now let's go and think about this production function. This is our new production function over here in that green box. That is a production of ice creams or vehicles or this final good. And there are going to be two inputs of production. K, capital again, and L, where L here is labor. Before it was N, Solo uses N, Romer uses L, but L is labor, N is labor, same thing. There is one detail that the AT, the technological or the knowledge parameter, is multiplying labor. So what Romer wants to assume is to think about technology that is labor augmenting, a technology that increases the productivity of the workers. Okay? Then there is another term here that is AK and AL. You can see that. So now I'm going to go to the next part. And what happens here is that AK is the fraction of capital that is going to the production of ideas. So capital, you have an amount of capital that is going to be divided into a fraction AK and a fraction 1 minus AKK. The first one, AK of K, goes to the R&D sector, to the production of knowledge, to the R&D sector. And this other fraction goes to the final goods sector. A, Y. And the same applies for labor. Labor, a fraction AL goes to the production of R&D sector, and a fraction 1 minus AL of L goes to the production of the final goods sector. So this is interesting because you can change AL, AK, and you will be reallocating capital or labor from one sector to the other. It's like if we want to take researchers to the production of automobiles, we can do it. Or if we want to take workers producing automobiles to the R&D sector to think about better ways to produce automobiles, we can also do that. So that's driven by the AK-AL. Okay, so that would be the only change was production function that we had before. Does it make sense? Okay, now let's go to the other production function. There are two sectors now. The final goods sector, but also the knowledge sector. And this is there's going to be an R&D sector that will produce ideas. And for convenience, we don't think about the production function of A. We think about a production technology that drives the change of A. Remember that A of T is just delta AT T. So it's the time change in A. The change in technology, the A dot, is driven by that production function. There is a B, capital B term that drives the technology of the idea sector. It's like, suppose we are researchers, and suddenly we get a really great idea. So this is kind of the trick, because it's like an endogenous growth model, but it still has an exogenous growth component there, which is the capital B. It's like we are today creating ideas, but suddenly we receive some idea from Colombia, from Singapore, and we're able to better produce ideas right away, better produce knowledge exogenously. However, there is also the fact that we are endogenously generating more ideas. If we're here thinking of better ways to produce, and some of us bring more capital, K over there, more computers, we're going to be able to produce potentially more ideas. So more computers produce more ideas. More researchers, more people in this room producing ideas also will increase the production of ideas. L over there, right? This is increasing in capital, is increasing in labor, but it's also increasing in the current amount of ideas. This production technology is assuming that if we all come here with no ideas versus we all come here with lots of ideas, there's going to be a different ideas generation process, right? And whether that is increasing or decreasing returns, that depends on the theta. If the theta out there is really small, that means that having lots of ideas today won't give us too much ideas in the future. It won't generate too much ideas. But if the theta out there is super large, that gives you like increasing returns to ideas. That if we have today good ideas, that explosively increases ideas, and we are super creative and generate a lot of good ways of improved production processes. Basically, this is a way to make the production of vehicles or the production of computers more efficient, right? More productive. Yeah.
What was B again?
B is a parameter that represents that anything like somehow a shock makes us everyone more or less productive. This could be actually, say,
Incentive for generation of ideas, for example.
As we discussed before, for the Jones case, the social infrastructure that was embedded in the term A, you can also think of that B term there as a residual that has lots of things that are going to make the production of ideas better. One might be what you're describing. Another way we can be thinking about is like so natural disasters or things that are going to affect the way we think we get together. Say, one way of thinking about that is that research department is located in Santa Lucia and the city is the automobile sector. And then the buses coming to Santa Lucia, somehow they stop coming because there is an accident, something like that. There is an accident. And that accident implies that just half of us get today or all of us get today. That would be better because we are not changing the L. All of us get here, but we get late. Right? And because of that thing that exogenously affects our production of ideas, that month we produce just a little bit because we were hit by that exogenous change in B that given our L, given our K, made us produce less A's, A dot.
So like the A in the previous one.
Exactly. That's why I said like this is an endogenous growth model, but still you got these exogenous shocks, which is not bad. I mean, the world is quite stochastic. I mean, sometimes you get a lot of these things. The other day actually happened something like that with the buses. When was that? Last Wednesday, Monday? Tuesday. I think it's Tuesday. Yeah. I don't remember, but it was full of people waiting for the bus, and at the end, people started to walk, and I walked 1 hour to my house and all that. So that productivity also is affected there, right? Okay. So, but as I said before, the theta parameter is going to be crucial here. Theta is how strong is the impact of current ideas in the generation of new ideas. If you think that ideas have some kind of diminishing returns, theta might be smaller. If you think that ideas have these huge spillovers, there are some evidence for California, what is Silicon Valley, right? Silicon Valley spillovers but then is it the case that they are still producing as generating as much as before, or there are some kind of diminishing returns there? We can test probably what is the value of theta, but the value of theta here we take it as given and we change it and we see how that affects the model solution, and it's quite interesting. Okay, so theta here is going to govern the diminishing or increasing returns of knowledge. And this is going to be super important for this model. Okay, so we're assuming that now that R&D sector has incentives to exist. Suppose if we were generating ideas over here, right? And we come up with a great idea that took us a long time, a lot of resources. And then we go out there and there are no patents. Then just somebody else will copy our idea and will extract the benefits of our idea. So we're not going to get any benefit of thinking a lot about our new ideas. So for new ideas to exist on the back of our model, there must be some patents. Romer has a more complicated model where he microfounds that, where firms that generate ideas have some monopoly power. Okay? Good. So we also assume that capital and labor are growing. Investments. So before we had KT plus 1 is equal to YIT, plus 1 minus delta KT, right? And then if delta is equal to 0, then we can write that down as KT plus 1 is equal to IT plus KT. Change that a little bit more, and you got that. And we also have that investment is just a fraction of output, and then we also have that by definition is that. So in our previous model, with no depreciation, we have that the change in capital stock is just a fraction of output, because that's investment basically. New computers, the change in KT, or change in KT plus 1, is investment, is new computers, is new machines. And that is given by a fraction of output investment up there. And here it's just the same, except that in continuous time, this is kind of, in continuous time, this is kind of delta KT, right? Or delta KT plus 1. And there is no depreciation there. You can think of intuitively, the time is so small, like 1 second, that capital won't depreciate from 1 second to the other. So you might think of this like connecting these ideas. I'm trying to connect that. And on the other hand, here you have that the amount of workers, L, is growing at a rate equal to little n. Just from that equation, you have this. That is the growth rate of labor. The growth rate of labor is the same as before, little n. Okay? Good. So now let's solve them all. Yes?
Shouldn't L dot T just be n?
L dot is the change, like the change in the variable, just the level change.
So it's not the actual derivative, it's the final result.
This is the time derivative, right? The time derivative, how it changes from today to tomorrow, and then divide by the current level. That gives you a percent change, right?
Yes, that should be n, what is it, n times LT.
You mean here? In this equation over here? That?
The one in the middle.
This one?
Yeah, why is it n times LT? Shouldn't it just be n?
Yeah, I mean, it's the same equation as this, as the one below. This one over here,
How you just multiply it?
this one over here is just bringing that guy over there, and it's just that equation. Yeah, the reason I'm writing down in that way is terminology in Romer's, but I mean, it's just the same thing. It's just L equals to NLT, which is just the same as the one that I have on the bottom left, which is the growth rate of L, is just little n. That's the idea. Okay, so now let's define one more thing, which is GA. As we said, L dot LT is the growth rate of L, which is little n here. The same thing applies for any other variable, so therefore A dot T over AT, that is the growth rate of knowledge. That is the growth rate of technology, and we're going to call that GAT. And that will be a key element in our model, how knowledge is growing over time. Okay? And how can we find that? Well, we can find it easily because we already have a production function for A dot. We just use that production function A dot. So this is the definition of A dot. This one over here. That's the definition of A dot. And let's just divide that by AT. When you do that, you get B AK K of T to the beta, where beta is a parameter that determines how important is capital in the production of ideas. And gamma is a parameter that determines how important is labor in the production of ideas. And there we have AT to the theta minus 1. that theta minus 1 in green just comes from the fact that we are combining this guy over here with that guy here in the denominator. We have at to the theta in the numerator, and we have at in the denominator, and that is just at to the power of theta minus 1, that over there. So it's just dividing the at dot equation by at. And this is just equal to the growth rate of A. Okay? So given that in tutorial you will also go over this math, I will try to skip a little bit of this because I'm just to focus more on the economics and the equilibrium effects of the long-run implications of this model. Okay? Let's go. This is just the same as I did before. When you divide a dot equation, the generation of ideas, by at, you get that equation over there. So this is a key question for all of you, for all of us, to understand the next steps. We want to think about long-run equilibrium. We want to think about whether this economy delivers a steady-state equilibrium. How do we think about that? So in the augmented Solow model, in the long-run equilibrium, per capita variables were growing at a constant rate equal to little z. So now let's think in the same way here. A long-run equilibrium is going to be an equilibrium where variables are growing at a constant rate, which means that GA is going to be just constant, a number, and also the growth rate of output per capita, G little y, will be constant. Think of a world like that. As in the augmented Solow model, that was our long-run equilibrium. Per capita variables were growing at a constant rate. We want to check whether this model also delivers something like that. So we want to see whether we find a value for GA that is constant. So we find our GA star. Here, rather than solving for levels, for per capita variables or per efficiency units, we're solving for a constant growth rate. If we are able to find a constant growth rate of knowledge that also determines a constant growth rate of output per capita, then we found a long-run equilibrium of this economy. Okay? So another way to think about this is that if we do find this equilibrium where GA is constant, if GA is constant, then it has to be the case that the delta GA dt is equal to 0 in the long run. If we reach that long run equilibrium where GA is GA star, that means that GA is not changing. Which is another way to say that mathematically is to find an equation that is of this sort. If we solve an equation like that, where GA dot is 0, that means that we found an equilibrium where the growth rate of A is not changing. That the knowledge is growing constantly in the long run growth. Sorry, in the long run. Does it make sense to everyone? Intuitively, if we were to find this long-run equilibrium with a constant growth rate, say in Australia, we look at the data, 1.7% with a nice trend. If we look at trends, the US 2%. Let's try to see whether this model delivers something like that. Then let's look for that equation. We're going to make some assumptions here. This is the more general case, but suppose, to simplify the math, and the same intuition follows, suppose that beta is 0. There is no capital in the economy. Suppose there is no capital at all. Therefore, suppose this actually disappears. is just equal to 1. And suppose it's actually disappearing is equal to 1. For now, which means that GA equation just simplifies to that, only labor in the mall. So remember, we want to find an equation that is GA dot. GA dot, that whether the change in that GA is eventually going to be 0, meaning that we eventually found a long-run growth rate for knowledge that also implies a long-run growth rate of GDP per capita. Is that what the model predicts? And here we can actually do it by using the same trick, this hint. This hint is actually quite useful in continuous time models. That's a hint we're going to use. When you take the derivative of the log of a variable with respect to time, there is a typo there. It's not dt. This shouldn't be there. That shouldn't be there. It's just d log xt. When you take the derivative of the log of a variable with respect to time, that is going to be equal to the percent change of that variable. Here, what is the derivative of the log of x? 1 over x. And then chain rule, we apply the derivative to what is inside the log, which is x of t. Therefore, times dx dt. And that is just equal to. So this is just an exact formula coming from the properties of the log is quite useful there. The derivative of the log is 1 over x, and then dx dt is just the change in that variable in continuous time. So x dot over x is the percent change. So that's the percent change. So then you can anticipate that we're going to use this hint to take logs of our equation and then derive that with respect to time. Because we want to find, again, whether this exists. Is it the case that the economy in the long run stop changing the growth rate? Is it the case that the economy just keep growing at a constant rate? That's what we're looking at. Okay, again. Let's do that. Let's take logs, take the real with respect to time, and the details are going to be in tutorials. The details are in those slides, so let me try not to focus so much on the math from now on. I've said that too many times, and I keep focusing on the math. Who likes that I focus on the math sometimes? Do you like that I do that, or you prefer me to skip in just the math? Who likes me to skip in the math? Okay. So, let's just get to the conclusions, and no. This is not a math class, but it has a lot of math. Okay. So let's apply the hint, take the logs. Take logs to that variable, to that equation over there. Here we just apply the properties of the log. No much math over there. Just applying the properties of the logs. Take the logs to the equation above. Good? Now, after we take the logs, we take derivative with respect to time. These two guys over here, they don't change with time. Not changing. So the derivative of that with respect to time is just 0. But labor is growing, and technology and knowledge creation is growing. So then, when we take the derivative, we only have this is going to disappear because the delta of that with respect to time is just 0. So then there is nothing of that here. And here, the derivative of that with respect to time is just derived with respect to time. And remember, now we apply the hint. When we derive with respect to time the log of the variable, then that becomes the percent change. Then we go to the next line, and then this is just equal to this. Applying the hint, this is equal to LT over L, L dot T over LT, which is little n. That is equal to little n. And when we apply the hint, that is equal to A dot AT, which is equal to GAT, the growth rate of knowledge. Okay? And then we also have, then we just apply that definition little n, so it's going to be gamma times little n, because the delta log n dt is just percent change of labor, which is little n. And then we're going to have theta minus 1 times GAT, just applying the definition. Simple. And then we have that is equal to GA dot over GA. What is that? That right-hand side, that equation, is equal to the growth rate of the growth rate. GA dot divided by GA. That is the growth rate of the growth rate. And that is what... now we have that equation. We have GA dot, and we have this left-hand side, gamma n theta minus 1 GAT, and we can try to see whether there is an equilibrium when GA dot is equal to 0. So let me go to the next slide. Here, this is just transforming and keep going with the previous equation. I just keep going with the previous equation, use the definition of percent change of labor, which is little n, and use the definition of the percent change of A, which is GA, and then now bring this term to the right-hand side to have our equation. I should actually have a name for that equation. I don't. What do you think? What do you think about this? Are we going to have a case where that equation is actually equal to 0? Suppose the simplest case where theta is equal to 1. Say theta is equal to 1. If theta is equal to 1, can we find an equilibrium, long-run equilibrium, where the growth rate is constant? Or can we find GA dot 0?
If gamma or n is 0.
Only if gamma or n is 0, right? If theta is equal to 1, we get rid of this term and makes everything easier. And GA dot is just equal to so only if population is not growing, then here we can find a long-run equilibrium. That's like the simple way to deliver that, which is not the interesting one, because we do know that a population and labor force is growing, is changing over time, right? It's not like the interesting case. But just to think about this, like, if n is positive, give me any growth rate of technology, say that is positive, and then what happens? You use that equation there, and G dot, which is the growth rate, how the growth rate changes, then this equal to gamma n GA is going to be positive, right? And then nothing stops the economy from there. It's like, let's start with some initial growth rate, GA, then G dot is positive, and so on and so on and so on. So in that situation, the economy is explosively growing and growing and growing and growing at very high rates in that situation, when population is growing and we start. But on the other hand, if we start at GA negative, the economy is imploding, 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 shrinking and shrinking and shrinking. So that's like unstable and explosive equilibriums. So theta equal to 1, you might find a long-run equilibrium like this if population is not growing. And how can we see that very easily is if we come back a little bit here, and that is the definition of, look at this. And this is going to be covered in tutorial, so I won't do it. But from here, you can see easily what is the long-run growth rate of knowledge when there is no labor force, when there is no growth rate of the labor force, and when theta is equal to 1. You can see that. You're going to see that in tutorials. But now let's go to a bit more general case in these last 5 minutes, probably. And let's think of an interesting case, which is this. If we think about the first term of that equation, and let's draw a graph like this. If we think of that, equation over there, sorry. Just that first term implies a linear relationship between GA and GA dot, right? If we were just to have an economy like that, we're going to have something like this, like a linear relationship, and with a slope. This is a case where theta equal to 1, with a slope equal to gamma n, if that were the case. However, if we have a case where theta being smaller than 1, when theta is smaller, let's say another color. The green case where theta is smaller than 1, even though the first term over there increases GA dots, we're going to have another term here that is going to decrease it, right? So there are going to be two forces. The first force that increases G dot, the growth rate, the change in the growth rate, makes the economy grow and grow and grow. However, when theta is smaller than 1, that second term is negative, and that is going to go to the opposite direction. It's going to shrink the change in the growth rate. And there we have this kind of concavity. Intuitively, that is, when theta is smaller than 1, there are diminishing returns to knowledge. Existing knowledge doesn't create too much knowledge. So when theta is smaller than 1, this is actually a concave curve like that is then going to cross that line like the x-axis there. And when that happens, we can actually find what is GA in the long run, GA star. And there we have a long-run equilibrium that is well defined, and it's going to depend on the parameters of the model. So we can just do it mathematically. Try to do it 1 minute right away, which is find GA star. Find GA star. And what is GA star? GA star is solving that equation by imposing this is actually true. Imposing that the change in the growth rate is 0, that means that you're imposing there is a steady state growth rate of A. So what is GA star? When we impose that that equation is equal to 0. And that will work, that will be actually consistent when theta is smaller than 1. But let's find out. Jordan, find it out without looking at the slides. Can you? Or you already look at it? So equalize that to 0. Equalize that to 0 and then find what is GA star. Good job. Once you impose that, you will actually be finding GA star. Good. Good. So once you impose, not only just solve it, but also change the name of GA to be GA star. Because once you impose that, you're looking for GA star. Okay. Let me just show you the result. The result is this. The long-run growth rate of the economy is gamma n divided by 1 minus theta. Let's just discuss the intuition these last 2 minutes before we finish. What is this saying? Gamma n determines how important are workers in the production of the R&D sector. A larger gamma n, or a larger gamma, or a larger n means that there are more researchers working in the R&D sector. If gamma or n increase, because there's going to be more researchers there, then that increases the long-run equilibrium, the long-run growth of the economy by generating more ideas and improving welfare by implying more income and GDP per capita. So it's quite interesting that it not only affects the level, but also affects the growth rate of the economy, having more researchers. But also, what happens if theta increases? GA star. As long as theta is positive and smaller than 1, an increase in theta will make the denominator closer to 0, which is going to increase GA star. And the intuition is that an increase in theta, when theta comes closer to 1, it means that knowledge has stronger effects in generating new knowledge than theta over there. When theta is larger, current knowledge generates more new knowledge. However, when that is equal to 1, that is too strong, that the economy is explosive. When that is larger than 1, it's even more explosive. We're going to have like a convex rather than a concave curve. Okay? So this is the interesting thing about the endogenous growth model that predicts that not only an exogenous change in Z affects the growth rate, also the production parameters of the knowledge creation, how many researchers are there, and depending on what is the value of theta, the economy is either stable, very stable, or unstable, like explodes. Okay? Okay, so that should be all for today. And we're going to be covering this more in tutorials. It's also in the mock exam. So I will probably focus in the next lecture, in the last 40 minutes, to solve the mock exam question related to this, so we can continue studying them all, okay, in a way that is more practical for you. Okay, see you next week.